US Physics Olympiad, year 2021, USAPHO, final round. Problem 2. The dark forest. Dark matter could be made of hypothetical extremely light particles called axions. Because individual axions are so light, experiments do not search for individual axions, but rather for the classical axion field formed by a large collection of axions, which oscillates as A as a function of t equal A0 sine omega t. This is analogous to how a large collection of photons can form a classical electromagnetic field. In the presence of a magnetic field B and an axion field A, the axion field produces an effective current J equal G A dot B, where we define A dot as first derivative from A by time D. The effective current produces electromagnetic fields in exactly the same way as ordinary current, though it does not come from the motion of actual charges. Experiments can search for axion dark matter using systems which are resonantly driven by this current. You may use fundamental constants in your answers, such as speed of light, c, h, that's a Planck constant, E, that's a charge of electron, G, that's a gravitational constant, μ0, that's magnetic permeability for vacuum, Kb, that's Boltzmann constant. You do not have to provide numeric answers unless asked. When asked to estimate, you may drop constants of order 1. The numeric values provided below are from standard references where h, c, μ0 and epsilon 0 are set to 1. To get correct numeric results, you must restore these factors yourself. Part 1. First, we will describe some physical properties of the axion field. A. Consider a single axion at rest with mass m. Find its associated angular frequency omega. This will be the angular frequency of the corresponding classical field when there are many axions. B. Suppose dark matter is distributed spherically symmetrically in the galaxy with a uniform density ρ. The solar system is a distance r from the center of the galaxy and orbits around it with a period t. Neglecting everything besides dark matter, find the dark matter density ρ. C. The energy density of the axion field is m square A0 square over 2h power 3 c. Find the axion field amplitude A0. D. The radius and the period of the Sun's orbit, as well as the typical axion mass are r equal 2.5 by 10 power 20 meters, t equal 7.1 by 10 power 15 seconds, m equal 1.0 10 power negative 9 electron volt. Numerically compute the axion field amplitude A0. E. In this problem, we treat the axion field as spatially uniform within a terrestrial laboratory. To verify that this assumption is reasonable, numerically estimate the axion field's wavelength, lambda, assuming the axions have the same galaxy speed as the Sun. F. In part A, you found omega by neglecting the axion's speed. In reality, the axion's finite speed changes the frequency to omega plus delta omega in the frame at rest with respect to the galactic center. Numerically estimate delta omega over omega to show that it is reasonable to neglect this effect. Next, the abracadabra experiment, where abracadabra is abbreviation for this one. Currently taking data at MIT is a toroidal solenoid with the inner and outer radius r in and r out and the height h. You may assume that h much greater than r out for simplicity. A superconducting wire carrying current I wraps n times around the toroid, where n is high enough to neglect the discreteness of the wires. A circular pickup loop with a radius slightly less than r in is placed at the center of the toroid. Part 2. Now we will find the axion signal generated in the abracadabra apparatus. A. Find the magnetic field B as a function of R inside the toroid due to the superconducting current. B. The superconducting wires lose their superconductivity when exposed to a magnetic field greater than B max. Find the maximum possible current I max that can be used and assume this current is used in later parts. C. Assuming that omega is small, find the magnetic flux Fb as a function of T through the pickup loop due to the axion field in terms of A0, G, omega, B max, and the dimensions of the apparatus. You may ignore any currents induced on the surfaces of the superconducting wires. According for them makes the problem much harder, but does not substantially affect the final result. D. If omega is too large, the result above breaks down due to radiation effects. Estimate the frequency omega c where this happens. E. Using the design values r in equal 0.5 meters, r out equal 1 meter, and h equal 2 meters, estimate the numerical value of omega over omega c. F. Let F0 be the amplitude of the time varying axion flux. Using the typical values, B max equal 5.0 Tesla, G equal 1.0 by 10 power negative 16 giga electrovolts in power negative 1, and your previous results, compute the numerical value of F0. Next, the pickup loop has inductance L and is attached to a capacitor, forming a circuit with a resonant frequency equal to the axion frequency omega. The circuit also has a small internal resistance R in series and is at temperature T. The axion signal can be detected by monitoring the current in the circuit. The main source of noise is thermal noise, which causes fluctuations in the current. Part 3. We will now estimate the sensitivity of abracadabra to oxyons. A. The oxyon produces a current which oscillates sinusoidally. Find the signal current amplitude Is in terms of omega F0 and the circuit parameters. B. Find the average value of the current squared, I square, in the circuit due to thermal noise. C. At any moment in time, the noise current is oscillating sinusoidally with a typical amplitude In equals square root from min I square, which is much larger than Is. However, the phase of the noise current also fluctuates randomly. so that after a typical time tc, its phase will be roughly independent of the phase it had before. Find an estimate for tc in terms of omega and the circuit parameters. Hint: at any given moment, the thermal noise current is simultaneously being produced by the random motion of electrons in the circuit and damped by the resistor. D. Suppose the experiment runs for a total time Te much greater than Tc. Roughly estimate the average amplitude of the noise current over this period of time. E. The axion is detectable if the signal current amplitude is larger than the average noise current amplitude, and the circuit parameters are L equal 1 millihenry, R equal 10 milliohm, and T equal 0.1 Kelvin. Roughly numerically estimate the time needed to potentially detect the axion. Hint: if your answer seems strange, note that in reality the axion's phase also fluctuates over time because of the effect of part 1f. In addition, we don't know omega ahead of time, so the experiment needs to be run many times. We ignored these effects here to keep things simple.